last webinar of the Master Your Design series. It's a pleasure to be here with you today. And today's topic is actually Precast and Infrastructure Beams. My name is Vlastimil. I work as a technical channel manager at StatiCa Asia and Pacific, and I'll be your presenter today. We're running on GoToWebinar platform. So for those of you who are using the actual application or using the web browser, all of you are muted by default. If you have any questions, please type them in the question panel, either in the app or in the browser. The whole session is being recorded, so you don't have to be worried if you miss something. After the webinar, we'll put the recording on our YouTube channel as well as the website. Let me turn off my cam. And let's focus on the agenda. So today we'll be covering an inverted T-beam, but not the global design. We will focus only on section of the beam. So what are actually the challenges engineer might face, and what even is an inverted T-beam? Such type of structure is usually used in either precast building structures or infrastructure. Yeah, so typically those beams are precast beams, precast concrete beams. Yeah, which then eventually speeds up the construction and potentially reduces on-site labor. However, this type of element, this inverted or double-edge beam, is actually quite interesting, yeah, because it doesn't behave as the regular T-beam, yeah. For this beam, it's kind of specific that engineers must ensure sufficient shear capacity without over-designing the reinforcement due to the limited space for reinforcement. Yeah. If we tend to over-design the reinforcement, then we would need to deal with congested reinforcement. Yeah. So technically, we are limited by space for reinforcement. The critical part of such element is actually the web-flange junction. Yeah, this part or this part. This part is critical because it is highly stressed and governs the shear transfer from flanges to the web of the beam. Yeah. But unlike for conventional T-beams, the flange actually transmits the loads to the web at the bottom edge of the beam, yeah, which then creates a horizontal shear flow along the junction. And if the shear transfer is not properly assessed, then we might face serious issues. One of them can be slippage between the web and the flange of the beam, cracking at the junction, especially premature cracking, local crushing of concrete, and all of this actually affects the overall stiffness of the beam. So in this case, I believe now we should all understand and realize that the classical approach described in the code is not enough, and as the code says, we shall use more advanced method. One of the most commonly used methods for dealing with such structures is definitely strat and tie, yeah, which is perfectly fine. It's proven by time. However, it has some disadvantages. Yeah, you have to know how to build the equivalent truss model. The process can become quite iterative, maybe even time-consuming, And most importantly, this method doesn't describe serviceability, serviceable limit state checks. For example, the crack width check or deflection check, which are really crucial for this type of structure. So instead of strut and tie, another approach is to use the compatible stress field method and idea StatiCa detail. Why? Because thanks to the graphic scene, you have a control over the detailing requirements. You can display the structure either in 2D or 3D. So in 3D, you immediately see the placement of the reinforcement, to avoid any congestion. Because of the nature of the method, the compatible stress field method, we work with stress fields. So we actually see the actual response of the structure. Moreover, we get all results for not just ultimate limit state checks, strength checks, but also for all serviceable limit state checks, including crack width, including deflection with long-term effects, for example. All of this ensures safe design. It gives you the opportunity to optimize the structure if necessary, and also it gives you the chance to work efficiently. With this, you can significantly save some time. So before we proceed with the actual demo, I prepared a poll that I would like to run. So now you should see the poll, and the question is, I'm interested in knowing how do you deal with inverted T-beam or other elements with non-beam behavior. I'm talking about discontinuity regions. Either you are quite happy with linear analysis in your global tools, for example, in ETABS or other tools. You may be satisfied with the strut and tie method. You're using strut and tie method, but maybe you want to change it, or you don't deal with such elements or neglect the non-beam behavior. Okay, I'm getting some results. So I'll give you 5 more seconds and I'm closing the poll. So I'm closing the poll and sharing the results. So 33% of you use only linear analysis in FEA tool, meaning you do the global design for 1D beam, which is fine, but then basically the cantilevered part of flanges are neglected because in FEA tools you work with 1D members only. 50% of you use strut and tie method, but you might think that it's time to change this. 17% of you neglect such checks. All right. Thank you very much. So actually now is the time for the practical demonstration. So let me jump out of the presentation and start the detail application. So there are many ways how to design such structure in idea StatiCa detail. I'll show you how to do that using a blank project. So at first we need to select the corresponding model type. We'll be using 2D detail. 3D detail is mostly for anchoring. And you can start a new project either by selecting one of the predefined templates, or you can actually select completely blank project, which is our case. So now it leaves us with fill in the 4th column, which is called per meter. So I can fill the name, description, select the design code. We'll stick to Eurocode with this one. And now the initial settings for material properties. So we'll be using concrete C4050. So I will select it from the library. reinforcement is B500B, which is fine. Concrete cover 25 millimeters should be fine. So I just click on create the project. Okay, so the user interface is quite easy. 5 steps, 5 or 6 steps at the top, guiding you through the designing process. Yeah, buttons in the top ribbon. In the middle, there's this graphic scene where we do not see anything yet, and on the right side, the property grid. So now we want to add a new concrete element. Yeah? Since we selected 2D detail, we'll be really working in plane only. So out of plane effects must be neglected in this case, which should be perfectly fine for our case. So if I want to add a new element, I'll click on model entity and select wall. Now all I have to do is to type in the proper parameters. So 2.25 meters width, 2.15 meters height. The thickness of the element will be 1 meter. It's essential to set this, the thickness for proper stress distribution in the structure, even though we're working in line only. And that's basically it. So now we have a rectangular and we want to make it a T-beam, yeah? Inverted T-beam. So how to do that? I'll select a model entity again and define opening. So the opening will be rectangular, yeah? The width will be 0.65 meters. The height will be 1.45 meters. And now we just need to assign a correct position. Yeah. So the master point for this opening will be master point number 3. And the insert point, the same insert point number 3. So now we have one part of the beam. All we have to do is to either define a new opening or copy the existing one and just change the master point and insert point. So in this case, it'll be master point number 4 and insert point number 4. Okay. And just like that, we have a T-shaped element in our application. So now we're gonna define supports. Yeah. Let me jump back to the presentation quickly. So for our case, we will use a so-called patch support. Yeah. This patch support is actually a point support with a specific area through which the reaction is transferred to the model. Yeah. So now I'm talking about this specific area, yeah, through which the reaction is transferred to the model. And the reaction can actually be applied either directly to reinforcement, see the links that are representing the transfer of reaction to the reinforcement of the element. If the reinforcement is not defined, specified, then the reaction is applied to concrete. And this type of support, patch support, actually represents 2 types of structures, or it is suitable for 2 types of structures, either for as a precast concrete lifting anchor system, or it can actually be used as a bearing of the inverted T-beam as indirect support system, which is our case. So let me jump out of the presentation back to the application, and we will apply the patch support. Yeah. So we'll go to model entity again and define patch support, select patch support from supports. So now we have to assign the effective radius 0.1. That is fine. It's on master element number 1. Master point will be number 7. And now just the coordinates -75 and -15 should be fine. So now I'll just copy it and assign it to the other side. In this case, I will release it from the X direction. So we'll have slide in support. Now I will just change the sign to +1, and that's it. Yeah. So now we define the supporting system for this inverted T-beam. As a next step, we'll add load-bearing devices. Yeah, as there will be in reality. So let's say this is an infrastructure inverted T-beam. So it will definitely have some load-bearing or transfer devices. So I'll go to model entity again and define a bearing plate. Defining a bearing plate for point support in finite element analysis is crucial because this prevents proper load distribution and actually it prevents local crushing of concrete. So we'll just set the width of the bearing plate and thickness. The thickness is there for the stiffness, so again for proper load distribution. Now we'll define it on edge number 5. It will be from end, and the position will be 0.325. All right, I'll copy it, assign it to edge number 6, and that's it. So now we will define loads. So I want to define a new load case by selecting the button from the top ribbon, and we see that the load case LC1 appeared in the navigator tree on the right-hand side of the graphic scene. So the first load case will be permanent load. So I want to define new load impulses. Of course, I have to define the self-weight of the structure. Then I will define point supports, yeah, to represent the girders that are placed on the beam, on each flange or each edge of the flange. So I'll define new entity, define a point load. It'll be on bearing device number, on bearing plate number 1, and the value will be 700 kilonewtons. Now I will just copy, same, and assign the correct transmitting device to bearing plate number 2. That's it. So now I want to do the same for variable load. So again, I will just copy it, change the load case type to, I will delete. So self-weight, I will change the load case type to variable and assign a correct value for the variable load. So 935 kilonewtons and 935 kilonewtons. Okay, that's it. I'm satisfied with the load definition right now. So now I want to create combinations. So I will select the combination button from the top ribbon. The first combination will be for ultimate limit state checks. So we'll stick to ULS and change the combination rule to 135 for permanent and 1.5, sorry, the factors for permanent and variable load. Now I will just copy it, change the limit state to serviceable limit state, characteristic combination for the deflection check with, of course, different load factors, 1 and 1. Okay, I will copy it again, set the quasi-permanent combination for the correct width check, and change the factor for variable load to 0.45, like this. So I have defined the geometry, supports, transmitting or transferring devices, bearing plate, and the loads. So the last I need to do is to define the reinforcement. I can do it straight here from the design tab, or I can go to the tools tab. So that's what I'm gonna do. Before I start defining the reinforcement, I have two options or two types of analysis that I can run before even defining the reinforcement. The first type is linear analysis. So in this case, it's indeed linear analysis without reinforcement influence. That's why it is possible to run such analysis even without the reinforcement definition. And what we see now is the stress flow. So those blue lines represent tension in my element, and red areas represent compression. So I immediately know how my structure will behave and to which parts of the beam I should assign the reinforcement. Yeah. The same goes for actually topology optimization. So now this may remind you Strat-and-tie method, but it's because it shows you again parts of structure in tension, parts in compression, but instead of strats and ties defined by the user, we work with stress fields, yeah, compatible stress fields. So now I know that this type of shear link or stirrup will be crucial. This will be crucial as well. Maybe I would need another bar in here. I can turn off this analysis and start defining the reinforcement. So I will click the rebar assembly, yeah, select a group of bars, and I will define the bottom links or stirrups at first. So the diameter will be 25 mm. I want to have the reinforcement on more edges. Now let me emphasize that again, there are several ways how to define the reinforcement for this type of structure. I will show you just one way, but there are for sure other ways how to define the reinforcement. Yeah. I want to have 8 bars in layer. It'll be on element W1, of course, and on edges 1, 2, 6, and 4. Yeah, I want to have closed links or stirrups. So I will type 1, spacebar 2, spacebar 6, spacebar 4. And now the proper anchorage type, because as I said, I want to have closed links. I will define the perfect bond. I can copy the first defined pair of links or set of links and just change the setting. So in this case, we'll be working with 32 millimeters diameter. We want to have again 8 bars in the layer, and we want to have it on edges 1, 7, 3, 8, and 1. Now we need to assign the correct position. Yeah, so I want to select first edge and define the correct position like this. Last edge, 0 value. So again, I have a closed link. Yeah. And now, because based on the linear analysis topology optimization, I expect tension in this area. It would be wrong if I don't add any reinforcement here, because I might face unsatisfying results. So I want to add a set of bars to the top edge of the bottom flange. So I will again select rebar assembly, group of bars, and now I want to have again 25 mm. Yeah. And I want to have it on outline or opening edge. I want to have only one layer with 8 bars in it. And I need to assign the correct position. I said I want to have it closer to the top edge of the bottom flange. So I'll change the concrete cover type from settings to user value, and the cover will be 400 mm. The last thing I want to change is the anchorage type for the anchorage check. So I will select this loop. All right, the last thing I need to do, I need to set the vertical set of links and select that I want to interconnect the reinforcement automatically with wedge supports. Since I just did that, the non-conformity message disappeared. So this is how you can define the in-plane reinforcement for the inverted T-beam or double ledge beam. And the last part is proceeding with the analysis. So the CSFM runs materially nonlinear analysis, meaning it assumes material non-linearity. So thanks to this, it actually calculates with the real reinforcement influence. Yeah, this is the main difference between the linear approach, as you're used to use from your global FEA tools, and non-linear design using the CSFM. Yeah. In the global FEA tool, what you get are stresses. Based on those stresses, the software actually shows you the required reinforcement area based on the formulas from the code. In Idea StatiCa detail, you input the real reinforcement, the nonlinear analysis calculates with the real reinforcement influence, and it shows you results. Sorry, maybe before I do that, because since this is quite a bit structure, I want to change the mesh setting a little bit. I want to make the mesh finer to see more precise results. So I select the settings button from the top ribbon, select mesh settings, and change the mesh multiplier to 0.5, save it, and run the analysis again. So as I said, now the nonlinear analysis is being performed. It consists of 3 steps. Preprocessor, when it does the meshing, it connects reinforcement with the mesh automatically. The middle part is the analysis itself. The last part, post-processing, checking the results. And we actually see the results. So this is the summary check. It shows us the expected behavior. In the left hand top corner of the app, we see the overall results. So utilization for concrete, utilization for reinforcement, anchorage, stress limitation check, serviceability checks, and the crack width check. So now we can go through the individual checks one by one. At first, I'm interested in seeing the stress in concrete. So I can turn off rebars, turn on the mesh, and to see the behavior of concrete. Yeah. So indeed, at the bottom edge of the bottom flange, we see the critical value for the stress in compression. That's where I would expect it. So the software shows you the actual value of compressive stress. We see slightly asymmetrical results. This is due to the anchorage type of the link I selected. As I said, there are multiple ways how to define the reinforcement. I tried multiple approaches, but I found out that this one perfectly reflects our needs. I can actually see the stress in reinforcement. Again, the behavior is as I would expect it to be. So again, this actually confirms my initial assumption of the structure's behavior, but I can be sure because I see the actual results. Yeah. I can go to the anchorage check. stress limitation check. We see that all checks are passing for now. The only one unsatisfying is the crack width check. So we see the crack width along the whole throughout the whole geometry, throughout the whole section, with the critical value of cracks. And if we hover our mouse cursor over the desired area, we see the actual value of cracks. So we exactly see how the structure will be cracked and where we can expect cracks. Yeah, of course at the junction for sure. Yeah, because we're mostly interested in the bottom part of the beam. We can actually neglect the top part. Yeah, this is not our scope for this type of the beam. We're interested in seeing the behavior at the junction, at the bottom part of the inverted T beam. Yeah. So we see the cracks, we see unsatisfying results. This is something that you cannot see using traditional methods. And of course, the last part is the deflection with the deformed shape. Yeah. Together with the deflection with long-term effects. Once you're satisfied with the results, we don't want to explore the structure more. We can create a detailed report. Yeah? So I will switch from check to report. The report is fully customizable. You can have brief, detailed, or bill of material as a type of support report. Sorry. So all I have to do is to click the generate button. And now the software actually prepares a comprehensive, detailed report. Okay, so we see everything we should see. So this actually makes your documentation a bulletproof documentation. All right, so we're actually getting closer to the end of today's presentation. So this was actually a practical demonstration of how to design and check an inverted T-beam in plane in section using more advanced method than traditional methods. So let me go back to the presentation. Before I present you this, I just want to quickly summarize why we should use the advanced methods, but I believe we already know that, right? You could have seen that during today's presentation. The detail application gives you control over the detailing of reinforcement. You see the behavior in the graphic scene. So you immediately see how the structure will behave, what is the expected behavior, and you get all the results for not just ultimate limit state checks, but also for all serviceable limit state checks. So even though if I use strut and tie method for the same type of structure, I would see all passing checks. I would compare the compressive stress with the design resistance of concrete. I would design reinforcement based on the tensile stresses, and I would think that my design is fine. However, we saw that the structure fails for crack width check. And this is something what you might risk if you don't use more advanced approaches. So actually, if you're interested in learning how to use the app more in detail, if you want to be guided, but at the same time you prefer some self-paced education, I can recommend our own e-learning campus courses that are available on the website. Anyone can study them. The courses are for free. You can select from multiple courses. Since today's webinar was about concrete structure, I highlighted the concrete courses. There's one for reinforced concrete elements, for pre-stressed concrete elements, and a course dedicated to our simple RCS application. If you prefer to be guided by a lecturer, you can always request an in-person or online training. All you have to do is to go to the website, to the support and learning section, and request a training for your company. So what's going to happen after the webinar? After the webinar, please fill in the short survey. Tell us what you liked, what you didn't like about the session, what could be potential next topics for any of the next webinars. Also, as I mentioned at the beginning, the whole session is being recorded. After the webinar, we will put it to our YouTube channel as well as to the website. So you might find the recording after the session in the support center. For those who don't use StatiCa yet and would like to try it, feel free to download a free 14-day trial version. Go into our website, ideastatiCa.com, and either click in the button in the right-hand top corner of the website or using the link that you see on the slide. And of course, if you're looking for specific information, I can recommend going to our support and learning section on the website, where we have multiple useful materials, be it theoretical background describing the method behind our applications in a very thorough way, knowledge-based articles, step-by-step tutorials, webinar recordings of previous webinars, etc., etc. What's ahead of us in terms of sessions and other important events? I would like to highlight and inform all of you that in October, so very shortly, StatiCa will release the next major version 25.1. If you're really interested in what's going to be there, stay tuned. I believe we have something quite essential for all ETABS users. So follow us closely, not to miss the release. And of course, after release, the major version will host What's New in StatiCa 25.1 release webinar. And that's actually all from myself for today. So I would like to thank you very much for your attention, and see you at one of the next webinars or live sessions. Thank you very much. Enjoy the rest of your day. Bye-bye.